Chapter 11 is on systems of equations. So let's start with some terminology. A system will be denoted with a bracket, meaning that the linear equations in those brackets are being looked at the same time. So it's a system of linear equations. So 2, 3, 4 at a time. A solution to that system is the ordered pair where the x and y coordinate are the exact same for each line. And typically that's only going to happen once, so they're going to intersect once. And that's the number of solutions. So option 1 is most typical where that's going to happen where they intersect once. Option 2 could mean that there are no solutions, or option 3 there are infinite. So let's take a look at when that might happen. So if we're talking about linear equations, here's two lines. Okay, I've drawn them and they intersect once. So this is an example of that first option where you have one ordered pair solution. Okay, so it happens once. If I'm thinking about lines and I want to see when I would have no solutions, and I'm looking at lines, thinking about the fact that one intersection point is one answer, no solutions would be when those lines then are parallel. Okay, because they're never going to intersect. So if I say no solutions, that's because the lines are parallel. Option 3 was infinite solutions. Okay, you can write infinite instead of writing the little infinity sign if you want. So I've got one place where they intersect, none when they're parallel. So infinite, meaning that everywhere is the exact same, meaning that this line and this line are overlapping. So they're the exact same line, just in a different form. So those are your three options, and we'll take a look at some of these examples. Okay, we can graph them to find out where they actually intersect. So we have graphed many lines. So to graph this first line, I'm going to start at the y-intercept, which is 1, and then use the slope, which is up 1 over 1, up 1 over 1, and I can go ahead and I can graph my line. Okay, I can go ahead and look at my second equation, which is also in slope-intercept form. I'll do this one in red, which is going to start up at 4 and have a slope of negative 2 over 1. So I'm going to go down 2 over 1. Down 2 over 1. So there is my red line. So the solution to this is where they intersect, so where the red and the blue are the same. So your answer is going to be this ordered pair, okay? And by the looks of it, mine's at about 2.5, 2. So I'm going to say mine's at 2.5, comma 2. Okay? It's kind of a unscientific method and a little bit in the fact that we're kind of rounding. Yours may be 2.2, yours may be more like 2.752. So this method can sometimes be a little bit tricky, but as long as your ordered pair matches where your lines go and your lines are accurate, you will be fine. So let's try another one. So example B, again I'll do my first line here in blue. So that's a y-intercept of 1. Okay, it's a slope of negative 3 over 1. So I'm going to go down 3 over 1, down 3 over 1. So here's my first line. We should be getting really good at graphing equations of lines. My second line is in standard form, so I'm going to use the staggered zeros method. So if I plug in 0 for x, then y would have to be negative 7. If I plug in 0 for y, x would have to be a positive 7. If you don't like that, you can always rewrite that for y, and there's no problem there. So 7, 0, 1, 2, 3, 4, 5, 6, 7 is here. 0, negative 7 is down here. And I'll connect my 2 here. Okay, so again, your answer is where those two lines intersect. So it looks like mine is at 3, maybe not even 3, maybe 2.2 and negative 1, 2, 3, 4, 5, negative 5. Okay, so again, not necessarily the most accurate method, but as long as your ordered pair matches your intersection, we should be good. And you should be getting things that are pretty close to mine. Okay, so let's take a look at example C. I'll do my first one here in red. So I've got an XY table again. That's going to be the two ordered pairs 0, 2 and 2, 0. And I'll go ahead and connect those. And I'll go ahead and take a look at my second line in blue. Again, I'll make an XY table. Again, if you don't like those, that's fine. You can just go ahead and rewrite those for Y. But the staggered zeros method does work really nicely in these situations. So I've got 0, 3 and 4, 0. And, ooh, this one was kind of tricky. Oh, that was a bad line. That was a bad line. Those lines, I would think, are probably going to cross eventually because this blue line is a little bit more gradual and this red line is a little steeper, so they're probably going to cross somewhere out here. Okay, again, another reason why this isn't the best method, but it is really good so that you can visually understand what we're talking about. So this order pair be 1, 2, 3, 4, 5, 6, 7, 8, 9, negative 9, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8, 9, negative 9, 9. Okay, so just be really careful there. The reason I knew that they weren't going to be parallel is because the slope of those two lines are not the same, and that would be the only time that those lines would actually be parallel. So we'll take a look at a different type of question that we might be asked. We might be asked to verify that 21,8 is the solution to that system. So remembering that an ordered pair is x, y, so I can plug in 21 for x in my first equation. So 3 times 21 minus 2 times 8. And the question is, what does that equal? Well, that's going to give me 63 minus 16, which will give me 47, which is what it's supposed to. So I know that it works in my first equation. Okay, so now what I want to do is I want to check it in that second equation. So I'm going to go 4 times 21 plus 5 times 8 and see what that equals. So that's going to give me 84 plus 40, which is 124, which is what I'm looking for. So I've now verified that it equals what they're supposed to equal, and life is great. Okay, so that's exactly what a solution means. It means that xy coordinate works in both equations, and that is the exact place where those lines then are going to intersect. This is more of the algebraic proof of what we were just graphing. Okay, so now if they give us the graph, okay, we want to write the system that represents that graph. Okay, so a system has those little curly brackets, and they give us our two equations. So we've got x plus y equals 0, and then we've got our other line, y equals 1.5x minus 10. Okay, so it gives us the equations. The system then is the combination of those two connected by the curly brackets. The solution, okay, is where they intersect, which they're telling me is at 4, negative 4. And then check your answer. Okay, so check it means prove it. Okay, so show that that works. So algebraically, what I'm going to do is I'm going to, again, plug in x and y to both my equations. So the first equation is x plus y, so negative 4 plus 4 equals 0. So that works. The second equation is y. So negative 4 equals 1.5 times 4 minus 10, and we want to know if that's true. Well, 1.5 times 4 is 6, so we've got 6 minus 10, which does equal negative 4, so that algebraically works as well. So you are checking to make sure that that ordered pair makes your equation true. Okay, if it made either of them false, then that would not have worked. And that is all we have for graphing systems of equations. We're going to start looking at other methods later, but for now, that's just kind of the basics of systems of equations. So go ahead, start your homework, and then bring questions to class tomorrow.